Um, we have the flange, W wide flange I-beam 12-inch depth and 65 feet per, or rather pounds per foot. Steel is structural steel A36, and I gave you the area properties of the flange. We need to calculate the design factor, and my design factor is very big because of the moments. So I need to make a correction. Actually, we'll go down by, so it'll be 3.5. If you got it correct, it should be 3.5. So I stated the equation was section modulus, flexure formula was section modulus, the maximum moment over this section, or between E equals B and C, section modulus in the table, solve for what the design factor, and with this 0, this becomes 3.5. Okay, I made up this problem, so yeah, it was a bit too big. Sometimes you ask yourself, is it really? I mean, it's an unusual big but for design factor. And then number 3 problem, we have what? A flattened on top section and a cylindrical section. I'm asking you to evaluate the stress over this portion and then the total angle of twist, meaning that you evaluate the angle of twist here and then this one. You've been here for test 1, say this is an untested part of the in the total angle of twist of the material cover. So and I'm providing you was the values, a table, calculate these coefficients C1 and C2, and a graph. I used the graph. I understand some of you prefer to interpolate linearly between neighboring points to the HR is closer to 0.7, a little bit bigger. So the maximum shear stress due to twisting on the flattened section, I mean, it has the same formula, but polar section modulus, now it's calculated using one of the coefficients C2 and the radius of the original round shaft. Okay, so here I have evaluate the radius. Do these numbers look or correct? Have you checked against your solution? All right, and I extract also C2. So evaluate tau max, and then angle of twist has 2 components: twist of the flattened section, twist of the solid section. For the flattened section, we use polar moment of inertia, the equivalent of polar moment of inertia, using the C1 value, and it's C1R, radius of the solid shaft or the round portion of the shaft, power 4 times that coefficient. And then, so this is it in radians, and then for the same length, solid round without any modification, you'd expect the angle of twist to be less, okay? And it is, at least qualitatively, they appear correct. And you add the 2, and it's like 0.21 or so. Do these numbers look familiar from yesterday? You saw the problem. Okay, so I need to make a correction to this. Thanks for the input. And yeah, we're going to this menu. All right, so go to notes and this guy, begin a new chapter. We're going to come back and do maybe one more problem on bending. Shearing stress in beam. So we covered the section stress due to bending. Now this is bending stress, and we go to the to where it shows the stress distribution figure like this one. Okay, and this is for the left hand side. You know, we move along. We start from the far left end of the beam, x-axis moving along, x-axis coincides with the centroid, and the stress distribution is as you see it here, and these are tensile compressive stresses. So for a beam that is it's bent with a positive moment, that will be a smiling beam, as we keep on saying, at least locally. So I have compression on top, tension below. And it goes through zero at the neutral axis. Now, what happens in addition to that tensile compressive stress, also have stresses that develop, and these are due to the variation of the moment. So I brought with me this bind book, and of course it has the pages. So if you bend the book, can you see what happens to the pages? They're in the beam theory, in order for the Euler equation to apply, you want to have a normal plane to the neutral axis to intersect the lines perpendicular. They don't stay perpendicular here. If I'm to glue the pages together, and if I'm to bend it, I'm trying to hold it. It's much harder to fold, to bend it really, even if I hold only this end. So since the beam is solid, then this difference in length has to be, or is associated, the prevented change of length with the top being compressed and the bottom being stretched. It translates into shear stress that is parallel to that longitudinal axis of the beam. Does it make sense? The book explains it using laminations. You stack maybe flat rulers, and I brought this book. I thought is the easiest to demonstrate the concept. So we have stresses, additional type of stresses in beams that could be significant for certain instances. So I have a shear. Looking at this diagram, it's a simply supported beam with a force that is not centered, but it results in a known shape of the shearing force. And then we have the bending moment diagram. It's sloped. So yeah, our concern is where the moment peaks, and we know that on the outer skins is where the maximum stresses occur. But you can have, if you're evaluating the beam close to the support, the net moment is less, but the shear force is large. So you can have failures occurring in a certain type of material like wood or short beams. The book has a list of cases where the shear force and the effect, the corresponding shear stress, are significant. Okay. So again, they develop because the changing magnitude of the moment, and the changing magnitude is the same anywhere. And coming from the equations, you'll see we're going to use the shear shearing force from the shear diagram. So this, at least this first step of the analysis, it's required to evaluate the stress due to the shearing force. Okay, so we agree that if we're to glue the pages together, which will prevent them from sliding relative to each other, we're going to see this identifiable. So we'll see this identifiable stress. But we know on an element in shear that you have stresses tail to tail, head to head on all four sides. So this is the top, this is the bottom of a rectangular beam that's bent with the shear force is shown, shearing force is shown. There's a positive shear. It's in the cross section. If it's external, it's up, it's positive, causes a rise to the diagram. If we are analyzing the cross section as we move along the beam, then this would be the collective effect of the shear stresses on this space will be the shear force. Okay, so this is if we delimit a little rectangular element, we're going to, starting with, we said this one that we can tell that experiment with the book. But we complete the element and we have them, like I said, head to head, tail to tail, head to head. And that's the way the stress element looks. We'll see that the shearing stress, or the shear stress due to the shearing force, varies. Of course, has to be zero on top. And most cases, which is fortunate, the maximum shear stress is on the middle plane, or rather the centroidal plane of the beam. Why is good? Because we have maximum bending stresses on the outer skins, maximum shear stress elsewhere that is away and in the middle, meaning they don't get combined, which is, again, it's a good thing. Versus, I'm anticipating, we haven't studied combined stress. So if I have bending and torsion, the maximum shear stress due to torsion is on the outer skin, the maximum bending stress is the outer skin. So we have, and likewise, if we assume compressive stress due to bending as damaging, so we have, they occur on the same spot. Does it make sense, the difference? So we have maximum bending stress on the outer skin, maximum bending stress in most cases occur here. Or at the centroid or near the centroid, depending on the shape of the section. I need to open the book to follow from the book. Again, this is my annotated travel prospectus when I booked the cruise. All right. So we're going to introduce a new property of area. It's called first moment of area, that allows us to evaluate, and then we'll prove the equation, or we'll go over the proof of this equation. That is the, like I said, first moment of error. So by the way, when are these type of problems important? And I gave you an example with shortened beams, or analyzing for stress beams close to their support. Moment is small, but you have as severe as further to in between supports shear stresses. So if you have wood is very weak when shearing the fibers, the longitudinal, and shearing stress of wood is pretty modest if you look at the stability at the back of the book. If we have webbed beams, thin webbed beams, like I-beams, wide flange I-beams with thin webs, things can happen along this. So it's strong in bending. We move the material on the outside to maximize area moment of inertia, and it goes with it down the bending stress, but it can become weak at the web. I mentioned short beams. There are fabricated beams. Composite beams likewise are sensitive. And then we have fabricated beams. So it could be the case where I'm using a board and I'm assembling two more boards to fabricate an I-beam, or you see T-sections. Have you ever been in an attic, like a residential houses? They have constantly, I've seen this, so 2x4 and another 2x4 to make for a T-section, and they are nailed together. Well, we can do analysis and calculate based on the shear force ability. How much shear force can the fastener, the nail, or the wood screw hold, or it could be the glue if you're gluing them together. What's maximum or spacing they have to be. There should be a minimum required spacing, or maximum required, should say, you go less than that. So yeah, designing or calculating fabricated beams. And the general formula to use, again, later in the chapter, it's the derivation for it is explained. So shear stress caused by this amount of shear from the shear reinforced diagram, shear stress is going to be that shear force times first moment of area, Q, which we'll define in just a little bit, divided by area, total area moment of inertia, divided by thickness of the beam at the plane of interest. Okay, so we may want to analyze it going from from the bottom to the top. And this is done in some sample problems to where you can see this that stress distribution. Again, that Q is the first moment of area, and how do you calculate it? It's the product between the area of the beam, of the cross section above, could be below, they should be equal, or they are equal. So area of the part of the beam that's above the plane where I'm doing the horizontal plane, I'm doing the analysis, times the distance from the centroid of the assembly to the centroid of that delimited portion of the beam. So if you look at this figure here, okay, so how is the first Q, the first moment of area, evaluated? So if I want to calculate the, I need to reach up. So we have the entire cross section with its own centroid, and then, well, this happens, it's the rectangle that's in the middle, and say I want to evaluate the shear stress caused by the shearing force along this line, and it happens to be through the centroid, right? So that capital Q is calculated as this area times the distance between the centroid of the entire piece, entire cross section, and the centroid of the portion of the beam that I'm delimiting. Does it make sense? Of course, I can analyze it elsewhere than through the centroid. Could be at a plane of interest where that joining happens. I said you can use fasteners, or could be glue. The problem discusses, or the book discusses the case of nail fasteners, for which we know the amount of shear force capable per fastener. We can also analyze it for if you use glue, or if you use weldments that are discontinuous weldments. Sometimes it's, or oftentimes, so they have one continuous weld, which takes forever to perform, and it unnecessarily strengthen the joining. You can do 1 inch welding and then nothing, and after 5 inches you do another inch. Discontinuous welding is called. That's commonly done in practice. The only issue is it does not provide water tightness. So if that's an issue, you need to maybe seal that area somewhere. Okay, so we defined the first moment of area. This is called partial area, and then we can have particular cases like you saw where partial area is half of the total area. And the book explains how you can, the steps to take to evaluate the first moment of area. It's essential to do correct representation of the section, and go through the steps. If it's not readily available, finding the centroid, first centroid of the assembly, possibly the centroid of the partial area. Areas themselves are really easy to evaluate. Okay. So, yeah, in order to evaluate that shear stress caused by shearing force, you need first to draw the load diagram, that is reaction to supports given the external loads, and draw the shear diagram, and then take care of the first moment of area, figure out area moment of inertia, and then thickness at the location, and that's it. I said that luckily for most practical cross sections, the shearing stress peaks at the centroid, but not as a rule. So there are some of the, like this section or this section like across, they don't follow that rule. So they might be again, for architectural appearance, you might see beams that are unusual. They are not best for load carrying, but again, you have to deal with it. Okay.
Question real quick, just for understanding.
Yes.
Up to figure 8.8, just getting my head wrapped around the area P onto it.
Okay.
As that I-beam right there, let's say I see that the only the top area of that.
You said 8.8 or 9?
I'm sorry, 8.8. Sorry, 8.8.
Okay.
So AP is calculated from the top half of that. Let's say if we had a force that's pushing up from the
Well, let me trick you to
just making sure.
let me trick you to this other figure because it's more representative. That was particular case where the area or cross section of interest was centroidal, but it's not always the case. So I may be interested in an area elsewhere than through the centroid is this one, right? So say I want to know for some reason, maybe this is where the joining happens. You know, I want to know what the shear stress is given the V from the shearing force diagram. You know, I have that. So to calculate that first moment of area, I need to get the centroid of the full cross section. Find the centroid. So I delimited here that I want to calculate tau on this location. I need to find this area, and then I need to find the centroid of this shape, and then this y is going to be the distance between the centroid of the full cross section and the centroid of just the partial area. Does it make sense? You get the same value q if you consider instead the lower. So I can find the centroid of a rectangle. This one here, it appears that they meant to say, you know, extending this all the way. I'm seeing it slightly below.
Yeah, that's my question.
Yeah, this should be slightly below than the neutral axis of the horizontal portion of the T. But yeah, you can work with the other portion. You know, we have equilibrium. Either take the above or below section, the shear stress at the same location being transverse plane should be the same. So you can work with this section, get the area, measure the distance from the center of the assembly to the centroid of the partial area, calculate Q, and then apply the formula. V times Q over I of the entire section over T, thickness at the where you analyze. So it should be here, although it's the same for this particular figure throughout the flange of the T. Okay?
Okay.
Is it clear? Yeah, thanks for making me explain things a little bit better. All right, so this is a sample problem. It's nice because they apply the general formula to evaluate for this rectangular section, to evaluate the shear stress at various locations. Of course, on the upper and lower surfaces is 0 because the area is 0, Q is 0. So I have area that is above is 0. Of course, you can say, yeah, if I take the area below, but what becomes 0 is the distance between the centroid of the total and centroid of the area that you're considering. So no stress as expected above and below. And then they take several locations centroidal and then moved above and below from centroid, apply the formula, and calculate the respective stresses, and plot this graph. Again, using the general formula, they produce this graph. They smoothen between several calculated points, and as you can see, it's maximum at the neutral axis. Okay, so it's maximum for this figure is maximum at the neutral axis, which makes sense because this is where, I mean, you cannot help beforehand, but yeah, for this rectangular section, it's maximum at the neutral axis, while the maximum tensile compressive stresses due to bending are maximum away, which again is a favorable thing overall. If you're to do this for a triangular section, likewise they evaluate or what the centroid is for the entire triangle, and that will be what? If this is 300 millimeters, this will be 100. You know this very well. It's 1/3 from the fulcrum of the triangle, and then apply general formula, and the shape of the shear stress as it varies along the vertical is like this one. It does not max at the centroid, it maxes elsewhere, okay? It maxes elsewhere. And then other shapes considered are the T, the I, and the cross sections. They don't go through the steps of how values to generate a graph were determined, but this is how they look. So yeah, it maxes at the centroid for this T section, yes, but there's a rapid jump like here, where the two rectangles are joint, and then in an I-beam, you see it goes up for the web. It's maximum to neutral axis, and remember, for thin web I-beam sections, this can be an area of weakness, where failure can develop through as wrinkling, or depends on if it's wood made, it may fail there. And then the cross with different thickness arms. So the shear stress maxes, as you can see, not at the centroid. It's actually small at the centroid or the neutral axis, but it's maximum where the transition between the two geometries happens. Okay. The next section explains how the that formula VQ over T times I, how's it coming from? Where does it come from? So it's from the equilibrium of an infinitesimally wide piece of the beam. Okay, so you have the beam and you delimit, you slice a small slice of the beam. So say you're here at x1, and then you move dx to the right. This will delimit the slice to the beam, and we have two moments, m1 and m2, left and right of the sections of that dx I-beam, and because there's we know one thing. We know that dm over dx, it's v to begin with. And in order to maintain equilibrium, because we have left and right stresses caused by bending are not the same because of this dm part. So m2 is m1 plus dm. Okay, we need to introduce, to maintain equilibrium, we need to introduce force, shear force. If we know the shear force, divide by area, which will be the shear area, longitudinal shear area will be what? dx times the thickness t, okay, gets us the full package to write equilibrium equation. So we have, like I said, equilibrium of that thin slice, vertical slice through the beam, m1, m1 plus dm. We have the shear force V, which is, assume, at some point we'll see that it's, or we saw already, it's not evenly distributed. But in any case, these in addition maintain equilibrium of the piece, because I have more moment here than I have here. So the difference, dm, is taken by this guy. And that's why this formula, dm over dx, is v. This translates into essentially equilibrium or balancing the increase of m by dm due to the shear forces on the vertical surface. And now, if we take again, assuming that we're interested in the shear stress somewhere here along this line, And I have, you can see I have YA and YB all the way to the top from the centroid YA. The plane where I'm, or the longitudinal cut along between where I want to evaluate the centroid. So it's going to translate this V4 into a shear force is shown. So shear force, it's the Fs is the unbalance between F1 and F2. These are the compressive or positive bending compressive stress that is more here than is here. Okay, so the difference has to be taken by the longitudinal shear force. Okay, so using the Flexion formula to define stress, normal stress here and here, and then if you take that and you multiply with the respective area, actually it should be an integral because that is is not constant. Okay, and shear force is the difference between the net force to the left and the right due to the bending stresses which are unbalanced, like I said. So you integrate to take F1, you integrate on the other side to get F2, and it gets us this for F1. Again, there's an F2, that the difference between the two gives you the shear force, and shear stress is nothing but that's Fs divided by what? By dx times t. Okay. So where were we? We have some constant pulling front here, moment of inertia and moment to the left section, and this is what? This is the centroid of the times the area. This integral centroid of the partial area times partial area. Okay. All right. So moving forward, I said that shear stress is going to be shear force by the horizontal section area, right? And we've got this difference introducing the we use areas and distance to the centroid. You saw it earlier. So we got next step would be to confirm the equation that was introduced as we saw it earlier. So that's a repeat of the equation before, does not have a number. So shear at that location, shear stress from the diagram, first moment of area, moment of inertia times thickness. If you're to calculate the maximum shear stress for certain sections, either going through the process of evaluating the first moment of area, or given some either exact or approximate equation. So if you have a rectangle, the maximum shear stress on a rectangle will be 3/2 shear force over total area. So if you have a rectangle, and again, this is an exact formula. So it says here where the exact maximum shear stress due to shearing force for a rectangle, it happens to be through the centroid. For a round solid bar, likewise, we have an exact formula, 4/3 shear force over total area, and it happens likewise at the centroid. And then we have a few approximate equations that are given, actually two of them. Just one. Okay. So if you have a thin wet shape, you can approximate the maximum shear stress, which happens here, with this formula. So shear force divided by where it says area of the web, so it's just the area of the web, not the horizontal area. So it says T times H. Well, H is shown as full depth. I sometimes see students using the actual, to calculate the area as with H being this much, not the full depth. Error are small. Anyway, so an approximate formula gives us the maximum shear stress for a thin web shape, and likewise happens with the centroid. All right. When it comes to doing design work for structures, so using recommendations from American Institute of Steel, AISC, American Institute of Steel Construction, I think it is, yes. So MAC design stress essentially limited to 0.4 of the yield strength in tension. And that's for steel. For aluminum, you limit it to what was it? N for aluminum now. Yeah, if you take N equal 2, so when working with aluminum on building-like structures, you want to limit the shear stress due to the shearing force to 0.25 times the yield strength in tension. That's the property that is already available. For wood beams, for concrete, for masonry, they have recommendations. Okay, so in catalogs of wood based on the wood grade and species of wood, they give you directly what the maximum shear horizontal shear force would be. Okay. Composites, there's being laminar and anisotropic. So likewise, they are weak in shear, prone to delamination, weak in shear. All right, let's look at this concept shear flow and how you can size fastener. I said that you can see fabricated sections. I gave you the example, pretty common. If you drive by a construction site and ask permission, or maybe after hours, you can just walk through to see how they put together 2x4s to make beams support the attic, the roof. Or a full I-beam, you use 3 2x4 each assemble and you drive nails. Question is what should be the spacing of the nails. If you know that, so we'll start for nails with what would be the shear force, allowable shear force per fastener per nail. And we're going to define what we call a shear flow. So shear flow, this lowercase q as the shear, so it has unit of force per inch. So I take force per unit area times distance, that gets me pound per inch or newton per millimeter. So this is the shear flow. Okay, so moving forward, using the general shear formula that we contemplated earlier, so we have the shear flow as being shear force times first moment of area divided by area moment of inertia. And because it's not very explicit, it gives us an example. So say you have, with an example, but this is the equation to use. So you have the allowable force per fastener, and you have the shear flow. It gets you the maximum permissible distance between two successive fasteners. If you take this force, allowable shear force per fastener, and you divide it by shear flow, calculated with this equation, gets you maximum distance. And of course, you round it to a preferred size. This one very well can go to 5 inches. Okay. Okay, so this was really the chapter. You'll master it as you know very well by doing, or will master it as by doing problems. So it's 49. I'm going to do with you some problems using the general shear formula. So I selected this, and was it 14? Yes. So we need to go through the steps of finding the centroids, and it says it's given as if or like for analysis that we're not doing at this level of problems, or for this problem. So shear force, for example, problem 813. You look at problem 813. So there's a generic or common text. Computer shearing stress, the horizontal neutral axis. And then for problem 13, it says the shear force at that location is 71.2 kilonewtons. Okay. Let me bring up the let me bring up, because I took screenshot, it's chapter 8. And let me download this, save image as downloads, okay. And I'm opening Paint and file, open, download. This is download. No problem, I can go straight to downloads. Cancel. I need a book. I need to go back to the book on occasion, so let me just downloads. All right. No, I want to open it with Paint. Open with. First time I'm doing this. Edit with Paint. Do they have Paint here? Paint. They used to. Yeah, here it is. And then I go to File, Open, and it should be. This piece. Down. Okay, got it. Right, so select all, and I'm going to select all, crop. I'm going to maximize it to where and screen must go up. All right, so I said problem 13. Shear force is 71.2 kilonewtons. The other one is an uneven T section, and the shear force is in the hundreds. Also a metric problem. So it says use the general formula. So general formula is, I'm going to state it here, so shear stress is going to be V is given Q, we need to evaluate it, over I over T. And it has to happen at the centroid of the entire figure. So, or just a little bit so that I don't stretch the left. Stretch myself. Okay. So the center, because of symmetry, we know immediately we know where the centroid is. So this is C for the section, and this is where we evaluate the shear stress. So we said that V is given. Can we tell T from the figure? What's T? Well, to be successful in solving a problem, you need to understand the problem, right? What is given, what you need to find. So is it T given? Is it on the board? Come on. This is T, right?
60 millimeters.
Yes, this is T. Thank you.
Still waking up, sorry. 60 millimeters.
Okay, let's evaluate.
I'm here, all right.
You're good. Either above or below, the partial area is going to be the same. We take the one above. Sometimes below might be easier to evaluate. Okay. So what we need to do is we will need I for the entire section at some point. We also need what is the centroid for the partial section, CP, I think they used it. And of course, what will be this distance? So in evaluating Q, remember Q is partial area times, was it y over score? I think it, yeah, y over score, the notation used. So AP y over score. So y over score is going to be this one here. Okay? And area, we can evaluate area. AP, is that correct? So AP for this section is going to be what? What is AP? Help me, take a, give a short break to my voice. What's partial area? Looking at the figure, what's the partial area? You don't need big deal maths to write that down. We'll calculate. Who wants to help? So it's made of two sections, a rectangle and half of a disc. Is that right? So I'm going to have half of 190 times thickness, so it's going to be 95 times 60, and that's for the rectangle. And then I have half of a disc plus 1 over 2 because it's half of a disc, and then the formula to calculate the area of a solid disc. So pi, and the diameter is what? 60 squared over 4. Alright, so we have here, where's my calculator? Alright, so 95 I said, that's 190 over 2 times 60 plus, we say 0.5 times pi times 60 squared over 4 equals. And this is 7,000 or 7,113.7, and these are millimeters squared. Okay? So this is what I have so far. We need to make use of a table like this to evaluate the centroid of the partial area, and then we need to repeat it for what? For area moment of inertia and of the entire thing. Is that right? So on one hand, we have only 2 entries. So I'm going to delete this. This is a table from page 365, a page that is easy to remember, although I told you to bookmark it. All right, so let's evaluate. Let me see. Let's evaluate area moment of inertia of the entire section, okay? So what is the area? Oh, we actually have 3. Why? I need to go undo because we have 3. Is that right? So let me move the copy. Let me move this down, paste, put it on reserve here above. So we have 3, again, we at this point we're evaluating this. So we're here. Do you follow or are you explaining to each other? I can leave, you can teach yourself. Alright, so we are working on finding I. We're here. So we have a rectangle and 2 half discs. There's symmetry. No need to go over we know the centroid where it is. So we have what? I1, that's for the rectangle. And for rectangle, area moment of inertia is the back of the book, appendix 1. It's used to have it memorized, but I no longer rely on my memory for certain things, and I know they are written down. So we're going to use Ix on page 753. So it's BH at power 3 over 12. So B, that is 60, and H is going to be the 190 over 12. Okay. Any more space? So I can stretch this. or do whatever. All right, so what is this value equal to? This is the rectangle. And then we have half discs. Two of them will have the same area moment of inertia. So 60 times 190 at power 3 over 12. So this is a pretty big number. Still not enough space. Copy and paste. Paste. Really need a lot of space, looks like. Hey, welcome. The survey forms?
Yeah, the pre-evaluation.
Which one? Pre-evaluation. I'm not certified evaluator. I was relying on you and your expertise. But you can do things.
No, it's just if you want me to focus on something in your class.
Focus on something in my class. Low attendance or low enrollment or what? I can take care of filling this out. Student interaction, like it looks like we changed the forms. I was used to the old ones, several pages.
No, the others, that's only the pre if you want to ask me to do something.
Okay, I can summarize just for you what we're doing because you came the second half of the. All right, so and you taught strengths and materials, right?
Yeah. No,
Okay. Yes
here
or no?
Here no.
Here, no, but you did.
Yeah.
So it's not foreign to you. Dr. Aref Masood is our colleague, and he's a certified peer or evaluator of teaching. So I'm shaking already. You know, I last time I talked to a certified person, it came up that I need to make some payments. It's about my house. Okay, so we covered, just finished, and we're looking at the first example problems. Covered chapter on shearing stress in beam due to the shear force. Okay, and we introduced the general formula, calculating the shear stress due to shear. This is the first moment of area. This is area moment of inertia entire section. This is the thickness of the section where we want to analyze. And this first problem requires us to use the general formula to evaluate the shear stress at the centroid. And in most practical cases, it's where the shear force, or rather shear stress due to shear force is max. We wrote the stated equation for the first moment of area. This is the partial area, would be area above, although we can take the one below, of the horizontal plane of interest. We want to evaluate shear. And this is the distance from the centroid of the entire section to the centroid of the partial area, right? And we're able to, this is given by the problem, thickness, it's on the figure, partial area would be a rectangle plus half of a disk. And now we need to use a table that's in the book, page 365. I said you write a bookmark where you know it's number of days in a year, regular year, not a leap year. And we have three parts like the table originally has. So for the centroid and total area, we're not going to go through those steps because it's obvious in this case. And we were, like I said, evaluating the moment of inertia, centroid moment of inertia of the first shape that is the rectangle. So that's 60 I said times 190 squared, rather power 3, I'm sorry, over 12. Oh, so 60 times 190 power 3 over 12. Okay. So I have, this is nice to be done in a spreadsheet, 3, 4, 2, 9, 5, and 3 zeros. And then centroidal moments of inertia of the half disk. And I think there are shapes on appendix 1 of the book. So we go to the back of the book. And on page 754, audio.com. So all exams are open books. So students are allowed to use the book during the exam because of the, the equations that they, alternative will be to allow them a formula sheet maybe, but then there's a lot of information at the back that they need to use. Okay, so I'm on page 754, and page 754 we have the, we're interested in IX, the centroidal moment of inertia for the half disk. So this is 0.12 zeros, and then 686 times, and diameter of the disk is 60, so times 0.00686, I said. Times, what was it, 60 at power 4. All right. So this one is, and I write it here for the second. So again, part 1 is the rectangle, part 2 and part 3 are the half disks. And for both half disks, I have the same number, 8905.6. Okay. And then for the parallaxis, to apply parallaxic theorem, I need to evaluate these distances. Okay. So the distance between the centroid of the assembly and the centroid of the big rectangle is 0. So this goes to 0. This goes to 0, and I repeat here 3, 4, 2, 9, 5, and 3, 0. This will get squared. One will be negative, one positive, but once it gets squared, it doesn't matter. So we need to know what's the distance from the centroid of the figure to the centroid of one of the disks. It will be the same with a negative number, negative sign that is for the other section. So we need to look again at the, I could bring it up, but I'm assuming you're on page 754. So the distance from the base of the half disk to the centroid, okay, it says here 2/3/pi times diameter, or 0.212 times diameter. 0.212 times diameter is 60. Okay, so this is, it goes here, it's 12.72. Units are, I can write in millimeter power 4. This is millimeters. This will be millimeter with power 3. This is millimeter with power 4. All right, and then the other one will be a negative number, but the same. We don't care once we square it, I said. Okay, so now I can evaluate these products. So 1272 goes on calculator screen. I erased it. 88905.6 equals. I need more space. Let's see how I can enlarge this. So copy paste. And delete this. Delete. Okay. I think I have more space. Of course, I need to shift this millimeter at power 4. All right. So what is the product between the and so this 1272 as a 1272 squared times 905.6. This is 1438478.3.8, and this will be the same 1438478.3.8. Okay. So yeah, here I'm just repeating 3, 4, 2, 9, 5, 1, 2, 3, and then I need to add this with this one. It will be the same number, so I still have this, add to this on here, so plus 889, which is 0.05.6 equals, so this one is 1,447,368.9.4. Likewise, and then I take this times 2, and then plus the value from above, 3, 4, 2, 9, 5, 0, 0, 0 equals. All right, so the sum, this sum here, which is essentially this value is 6,324,237.8.86. I'll say 9, ending in 9, and it's millimeter as power 4. Okay, so this is the total area moment of inertia. Yes, question.
Where did you get the 12.72?
Where do I got this one? So this is the distance from the centroid. I need to bring up probably be able to observe it. So if I go to the appendix or
Look on page 7.
yeah, appendix,
Semicircle onto it.
and then this one. Okay, can you see it? So we're dealing with a half a disc, and we're interested in the distance between the centroid, well, figures in paint, the centroid of the entire figure to the centroid of the half disc. Let's if I made a mistake. It might be. Back here, and it should be equal to this amount. And I think you spotted a mistake, so this should be 95 plus, what was it, 0.212 times diameter. 0.212 times the diameter. Diameter is also T, so I think this one here, it's only 12, it's just this piece. I need to add 95. So you're paying attention, or inadvertently you pointed to a mistake. So 12.72, 12.72 plus 95, it's so 1208.4, and this negative 1208.4. So what will that change? I have this, well, all are compromised. I need to erase this. I need to erase this. And so I need to square this distance and then multiply it with the area. So never wrote the areas. Area for the first part is going to be 60 times 190, 60 times 190. This is 11400. And then for discs would be essentially this piece here. So pi times 60 squared over 8 equals, so this is 1413.7, 1413.7, and okay, so I can make the necessary corrections. I keep this value in 2, or multiply, that is times 1208.4 squared equals, so 2064352 064352220. Okay. Yes. So I'm taking this piece and add it to this one. Still have it plus 88905.6 equals. So it's 20644412226. 4441226. So I take this by 2 and then add this one. So it'll be 343429512 equals. Huh? Oh my. I forgot to press. That's okay. Plus 20644412226 times 2 equals. Yeah. So we're making a change here. A lot of digits. 4163177 6.52 millimeter power force. So this is the area moment of inertia of the entire, it says T total, we can use T total here, so essentially we have this part of the equation to figure out. What is left is to evaluate first moment of area, so we need to find the centroid of just the top half or the bottom half, doesn't it? Questions? Yes.
Can you, on DI for the circles,
Mm-hmm.
is that 1208?
It's 1208.4. So what is it coming from? This piece here plus half the height of the rectangular piece, which is on the drawing.
How could it be 1208 if the whole object's only 200?
I did some multiplication, I did something wrong. So it should,
I got 17,
okay, so let's take care of this. It's 0 point from the appendix. 21.2 times diameter. 21.2 times diameter is 60. And then plus, and I have this piece. Half of 190, that's 95. But yeah, you're right, it's a good check, 95, cannot make sense. I wish I had this placed in a spreadsheet, I'm doing too many mistakes to my comp. So, 0.212 times 60 plus 95 equals, that's 107.72 is what you have. Okay. So I'm changing this, looks like I need to,
Everything else, yeah.
yes. So what is this changing? It's changing this by, they are horribly big numbers, and I started getting concerned just for that. So 107, but yeah, very good check. You look, it did not make sense, the value, negative 107.72. So I get it, I square it, so squared, and then times will be this area. Is this area correct value? Do you follow? If you have the luxury to work with maybe MathCAD or something that you can see that go back through calculations. All right, so I square this and I'm multiplying by, so times 1413.7 equals 16404,007.1. 404,007.1. Yeah, it looks like I squared this. At some point I was concerned I did not square this guy. Okay, so we can just to this add this value. Oh, I'm sorry, this value, and then take it twice and add this. It's almost 15, so we did this before. So plus 88905.6 equals times 2 equals plus I1, that is 34295.123 equals. Okay, maybe this one is good. 67280825 millimeter at power 4. The total area moment of inertia. So yeah, now looks like we're close to having the correct value. T is known from the figure, 60 millimeters. And then I'm left, like I said, to finding first moment of area. I need the area above the line, the section where I'm evaluating the shear stress. So another exercise of centroids. We need to adjust the centroids. So I'm going to lower this. Okay, we have only 2 parts, and I don't care about this second half of the table. And let's see, can I go all the way back? I can stretch a little bit. So distance to the centroid. Okay, so let's populate this this second table. I have well, part 1 and 2. Part 1 would be just a small rectangle, part 2 would be the half disc. And we have some values already. So for the full area, I have it, all I need to do is just divide it by 2, so it would be 114. Well, I could multiply 60 by 95, which is half this. So 5700, and then for half a disc, I have it calculated 143.7, and then I'm taking the datum for this problem. So this will be that, or this part. So this will be datum for this part at the centroid. So what is the distance I1? What will be distance I1? It's good geometry, folks. Unless you're ahead of what I'm doing, or you slow taking notes, which is, there's a remedy, you just take photographs and watch again the, Dr. Masoud, I'm recording the class for a student who cannot make it. He's working, he's retaking the class just to be able to graduate.
Class for one is
Hey Eric, we're talking about you.
47.5.
Okay, so you do what? So the distance from the datum to the centroid of the half rectangle is going to be half of 95, or 190 by 4. So 95 divided by 2, this is 47.5. This is what you said?
Yes.
Thank you, 47.5.
Next one's 95 plus,
Okay, let's see where that number is coming from. I just explained that, just for the rectangle, which is part 1, so I kept the labeling, is going to be this distance, 95 divided by 2. I need to go from here to here, and I think we've got this valued at some point. Isn't it this one?
Yes.
I think it is. So 107.72. 107.72. All right, we can evaluate this product and then take their sum and evaluate total area. Actually, I can do total area. Well, we'll do it some. So I have 47.5 on the calculator screen times 5700 and 270750, and the other one is 1413 times 107.72 equals, and this one is 152283.8. Okay, so to this one I'm adding the earlier one. Should have done it as I was punching the numbers, plus 270750 equals. Alright, so I have this 423033.8. These are millimeters to the power 3, millimeters and millimeters squared. Alright, so I have this, will be this part of the equation, 423033.8, and I can say over, open a parenthesis, will be 5700 plus 1413.7 close parenthesis equals. So I have 59.467, I'll say 59.5 millimeters. Never populated this, but I can say. Okay. So is it clear what I did? All right, this is Charlie Brown. You saw this in this part heavily in stats, calculating centroids. There might be shortcuts just because we have two bodies. But yeah, we use the table that's provided in chapter 5 of the book. And now that we have the distance from the centroid, the big centroid, to the centroid that is y score, this is our lowercase y over score, we can calculate first moment of area. So Q, let's see where I can put it. Q is going to be AP, we have it here, times Y over score. AP is this sum, and then Y over, so there's no way I need to evaluate this sum. 5700 plus 141.3.7 equals, alright, so this is 7,113.7 millimeters squared times Y over score 59.5 equals, and this is 423,265.2 units of millimeters at power 3. So really we have everything to evaluate after so much labor to evaluate shear stress caused by the shear force. Again, this is given in the text of the problem. We need to work, remember, to get shear in metric, in megapascals, you need to work with millimeters and newtons. So I have kilonewtons, I need to turn that to newtons. So 7, 1, 2, and 2 zeros. That's the force. Q, the second moment of area. I still have it on my calculator. I keep on saying this because these are little tips that save you seconds in case of the FE exam. That's why it's good to the FE exam calculator to be your everyday calculator. Who said that uses a TI that is sluggish? Somebody in this class told me the other day that TI 30.
Maybe it's Luke, I don't think he's here now.
Maybe. Okay, so 42326.5.2, and then below a lot of numbers. So a lot of numbers, like for the entire weekend and the week after. 280825, and then the thickness is 6. Okay, so I still have this times 71200 over 60 over 67280.825. All right, so we've got tau is, so working with newtons and everything millimeters or millimeters squared cubed. I have 7.46, I could say 7.5, 7.47 megapascals. This is a big value. Can we live with it? We don't know anything about the beam, but based on what we saw before, it's not going to cause damage. Probably a wood piece would it? No, not the wood piece. They said that it will be up to like 90 psi of shear stress in a wood piece that could be held by a southern pine material. Anyway, so yeah, we've got one first problem solved. Let's see, it's 128. We might be able to do a second one, or maybe at least discuss the steps. As you can see, it's numerically intensive. There are problems. Luckily, there are problems. You saw it. What are the sections for which we can evaluate the maximum shear stress caused by the shear force using readily formula, either exact or approximate. Okay, but this wasn't one of those. All right, any comments, questions, objections to the number? You've got different numbers.
Double check right now. I think I messed up. I think you're right.
Yeah, this makes for maybe a good computer-based assignment, homework assignment. All right, so I'm you want to take a picture of the board before I move to the next one, just to discuss the steps? You're moving too slow. You want to help me rest my voice?
You have glare.
This will be on
Your picture.
this will be on YouTube anyway, so you can go back anytime. I even tell students that they can play YouTube like 25, even 50% faster and still make sense of what is discussed. So let me open this. Actually, it does not work. I need to file new, don't save, file. And we're talking about this other problem. So where the shear force is 675 newtons and the cross section is I need to raise the board first. Well, I could have saved the equation, Lucas gave it you. All right, so this is an asymmetric T-section, and likewise, we need to evaluate the shear stress on the horizontal plane through the centroid. So this full package, we need to get the table like this employed to find where the centroid is. It's going to be closer to the, so it's not at the, like where? Would be 30 millimeter from the base, will be further up. And then I need to find the centroid. So this will be C total, and this is for the partial, centroid of the partial area, right? And so what is C will come up from analysis like this one, and then what is CP will repeat the analysis with only two bodies, like this one. It will probably go faster because we have rectangles. So let's see, we select all, crop, and working with millimeters, there will be a lot of decimal or numbers in the analysis. Okay, so for the early equation, we had it here: shear stress, shear force for moment of area, I over thickness, and then moment of area, it's partial area times central distance from the centroid of the entire piece to the centroid of the area that you consider a partial area. Again, you can take the lower area. No mistake by doing so. It might be more convenient. So if it's a T section, for example, I would definitely go for the lower, take this partial area, the lower area, because it's just one body or one shape. Okay, so this is going to be our Y over squared. Okay. So parts 1, 2, and 3, and then what will their areas be? For part 1, it's 5 times 50. That's 250, and these are millimeters squared. And then part 2, that's the bottom short. Was it width? Was the definition 20 times 5? That's 100. And the top part is 40 times 5. That's 200. Again, all millimeters squared. What are the distances? We're going to take the datum like so. So distance from the datum to the centroid of the first shape for the web is going to be 5 plus half of 50. That's 25 plus 5, that's 30. For shape 2, small horizontal rectangle, that's going to be half of 5, that's 2.5. And then from the datum all the way to the centroid of the wider flange, that's going to be 50 plus 5 plus 2.5, so 55. 2.5, that's 57.5. 57.5. Okay, we can now evaluate these products. I still have this times 200. So this is 11500. 2.5 times 100, 750. And 250 times 3, that's 750. 750. Okay. Let's look at these are the centroidal moments of inertia of the three body. Centroidal, well, relative to their own centroid. And I'm anticipating large numbers here. So I'm going to just say copy and paste and clean one of these. All right. So we saw this before. It's BH at power 3 over 12. This is appendix 1, page 783, or rather 53. So BH at power 3 over 12. So for the vertical, the web, we have 50 at power 3, we're at 5 times 50 at power 3 wholes over 12 wholes. So this is 5208.3.3, and these units are millimeter to power 4. The other two rectangles, one is 20 times 5 at power 3 over 12. 2083, and the other one is 40 times 5 at the power 3 over 12 for 16.7. Let me double check the first one. Maybe I missed that. So again, 5 times 50 at power 3 wholes over 12. 52083. Right, done. Okay, so next step is to extract from the figure the distances from the, well, I need to evaluate the centroid of the piece first. So sum of areas, it will be 250, 350, 550, like right here. And then sum of, so I have 750 plus 250, it's 1,000. And add it to, so it'll be 12500. Okay, so I can calculate the centroid. I think I took this outside of the viewing area. So it's I cropped this off, it's out. So it'll be what? It's the sum of what I have, A times I over sum of A. So over sum of AI, and this is 12500 over 550. Okay, 12500 over 550. This is 22.73. Millimeters. Is the correct value? It does not look right. So it has to be bigger. Maybe you missed something. So it should be bigger than 30, and it's not. So let's verify. What have we missed? Areas, I believe those were okay. I think so if you look at eyes, so one was 5 plus 25, 30. The other one is this, and the other one is 55 plus 2.5. I'm sorry?
The first AIYI is wrong. The 2
This one?
times 30 needs an extra 0.
This one needs an extra 0?
Yeah.
Okay, 250 times 30. 7500. So this changes, well, this stays the same, it's good, but we didn't have we're here and realized we need to, okay, so take this off. And, sums would be, okay, plus 250 plus 11500. This is 19250. 250. And this will be now the over or the correct over 550. And it's 35. It's a better value because it goes above the what will be 5 plus 25, 30, so it's bigger. Alright, so we're here, we can evaluate the distance between the centroid of the figure, and that's going to be this distance. Again, this is 35 millimeters, and now moving where? Back to the centroid of the individual pieces to get the DIs. So for distance from the centroid of the assembly to the centroid of just the vertical rectangle, there will be 35 minus 30, that's 5. Distance from the centroid of the assembly to the centroid of the first piece, that's going to be 35 minus 2.5. So that's 32.5. And then distance from the centroid of the assembly to the centroid of piece number 3, it's going to be, how can we go? We take 60, subtract 35, and then subtract 2.5. Am I right? So let's see, this must be equal to, I have, so 35, all the way to 55 will be 20. Okay, so I have 20 plus 2.5, 22.5. Everybody agrees? Huh? Okay. And now I evaluate this cross or area times distance parallaxis theorem, remember? So 250 times 5, it's 1250, 100.
You didn't square your five.
Oh, I didn't square it. You can tell it's 2 o'clock, near 2 o'clock. You had your lunch? Lucky you, I'm on what?
We're here, man, we're all dying, we're here.
Intermittent fasting. But that's okay. Yeah, you have a better perspective. But I'm covering the projector or the rather camera. Yeah. So 5 squared, that's 25 times the area 250. That's 6250. 50. The other one would be 32.5 squared times 100, and this is 1,05625, and then the 22.5 squared times 200. This is 101,250. Okay. All right. So to find the total area moment of inertia, I need to add essentially this, and I need to add this column. So this column that I need to add, and this column. I still have this guy, and plus I'm adding 1,05625 plus 6250 equals, got this taken care of, and I need to add these, plus 5208.3 plus 208.3 plus 416.7 equals. Okay, so total moment of inertia, air moment of inertia is 2658, 33.3 millimeter power 4. So it says IT, we're going to, it's hours here, so we took care of this. What is the thickness at the area of interest? What's the thickness of the area of interest? So checking your calculations against mine. Okay, so thickness is, who wants to help here? Come on, this is an easy question. I asked it before. So you've solved the problem, you don't know what your,
I got the same thing for the moment. Is that what you're asking?
you've got different numbers here?
No, it's the exact same thing.
Same thing.
Okay, all right. Well, sometimes miracles happen. So thickness is going to be, again, we're at the centroid of the assembly, and the thickness is 5 millimeters. So we have this one. This is 5 millimeters. And then we have, given the shear force, 675 newtons, and of course we need to look at the first moment of air. The partial area, it is what's above the, we can go with what's below the centroid, we can double or convince ourselves that we get the same numbers. So what's going to be AP? We can get it from, by looking at the figure. So what two shapes we have?
Bottom section and the middle.
You want to work with the bottom section?
I'd like to work with the top.
Oh, the top one, like the book does.
Smaller, yeah.
Well, maybe it's a like natural tendency to move up. You go up. So yeah, we have 20 times 5 plus 40 times 5. So it'll be 20 times 5, this one plus 40 times 5. So 100 plus, well, will be 60 times 5, right? That's 300. And units are millimeter squared. So we have this. All we need to get is the distance from the centroid of the assembly to the centroid of the just the partial area, which is the, you know, I crosshatch. I need to add some more to delimit AP. So that's AP. Okay, this is AP. I think we can erase this. All I need to save is just the moment of it. So I write it here, 2658. 265833.3 millimeters power 4. And I'm going to erase my writing, and I'm going to repeat for two bodies. I don't care about this part of the table, and I don't have a third body, but I want, in order to calculate where the centroid is of the partial area, that y overscore there. So part 1, I erased it, but no big deal. One of them was already, it was part 3, I erased it. So part 1 area is going to be the little rectangle, will be 5 times 20, that's 100. Do you understand what part 1 is? Part 1 is just this little rectangle.
Yeah.
You know, what is left of the old part 1. And then we have part 3, so part 3 is part 2. Or maybe I can do this. We don't have a part 2, we go to part 3. And that was there, so it was 5 times 40. That's 200. Okay, the new datum is going to be here. So the distance from the new datum to the centroid of this small rectangle is going to be, vertical rectangle is going to be half of 20, that is 10. And then the distance from the new datum, which is the centroid of the assembly, to the centroid of the horizontal 40/5 section is going to be 22.5. 22.5. Okay, so we can evaluate this product, will be 1,000. This other one, 200 times 22. And this is 4,500. Okay, and now we're good to find the centroid, again, will be our y, lowercase y over cent. So will be, sum of AI. So Bob, I have 1,000 plus 4,500. Below I have 100 plus 200. Okay, so this plus 1,000 over 300. And doesn't make sense. So 4,500 plus 1,000 equals over 3,123. What is this? Did I miss anything? So, okay, and I add these two, is what I do, and then divide by sum of areas. That's how it works. 300. I don't get a reasonable number.
What'd you get?
Like a lot of millimeters. We need to be what? Less than 20 millimeters.
I got 18.3.
Working with these
Yeah,
Figure
those
C.
are those exact numbers.
means I'm. So you said 18.33
33.
millimeters. Yeah, this makes sense. It's less than 20. So yeah, what do we anticipate? Okay, so yeah, looks like I punched numbers the wrong way. So we have y over score, and we can calculate q. So q is going to be the area 300 times 18.33. So 300 times 18.33 equals, that's, wow, close to 5,500, very close. I'm tempted to just write 5,500, 5,499 millimeters at power 3. Okay, so we have this. And we can evaluate the, finally evaluate the shear stress. So 52. We need to stop here. I had in mind another problem moving to where ready available equations for maximum shear stress are given. Okay, so this guy times 675 equals over 2,658, 3.3 over 5. And this is 2.79